Okay, so this is day 13, the last day of new chemistry content before our advice panel strategies for success session tomorrow. So today we're going to be talking about nomenclature, which the word nomenclature really just means how to name stuff. So we've been talking about all of these molecules and compounds for the last couple weeks. And how do we refer to them in words without using just the line drawings or the chemical structure? There are so many rules, so many words for stuff, so many names to remember. I think you can study nomenclature for weeks and still have groups and names that you haven't heard before or haven't memorized. So the goal of today is just to get some familiarity with some of these words and some of the nomenclature, so it feels less like a foreign language, so that if you see the name of a compound, you're not just like, I have absolutely no idea where to start. That said, we only have an hour, so we're not trying to memorize all the words and be able to name any given compound we see on site. I'm really just trying to give you a taste of some of the nomenclature. So we're going to start with ionic compounds. So we've been dealing with salts and charged compounds the last couple of days, so I decided to start there. So just as a reminder, when we're looking at the periodic table, the first column is the alkali metals. They're +1 when they form ions. The second column is the alkaline earth metals. They're +2. The second to last column is the halogens. They're -1. And that last column is noble gases, which are largely inert. So they don't really like to form ions or bond with anybody else. So today we're going to start dealing a little bit with the transition metals. Often these transition metals can exist with multiple different charges depending on who they're bonded to. So for example, chlorine is a halogen. So we can figure out the charge of chlorine. And then these two different molecules can both exist, CuCl and CuCl2. So we can figure out the charge of copper based on how many chlorines it's bonded to. So if chlorine is a halogen, it's always going to be -1. That we know for sure just from our rules from the periodic table. If CuCl exists, and that is charge neutral, and there's only one copper for every chlorine, then copper must have a +1 charge in this case. But in this other molecule, CuCl2, if there's 2 chlorines for every copper, then copper must have a +2 charge. So some of these transition metals can exist in multiple different charges depending on what molecule they're part of. But you can always figure out their charge based on what they're bonded to. Does anyone have any questions on this? So this is all tied back to what we were doing when we first introduced ions on day 5, but also the last few days with figuring out how many of each type of ion we need to end up with a charge neutral state. So when we are naming ionic compounds, we start by just naming the ions. So for monoatomic ions, they contain one type of atom. So mono means one, atomic is atom. So monoatomic ions are just one atom. And so the way we name monoatomic cations, we don't change anything at all. So sodium is Na+, it's in that first column, it forms a +1 charge, and so we just call it a sodium ion. So that one should be pretty easy to remember. If the element can form multiple kinds of charges, so like copper that we saw on the previous slide, so these are the transition metals, then we have to specify what the charge is in this case. So if copper is forming a +1 charge, we call it a copper 1 ion. If copper is forming a +2 charged ion, we call it a copper 2 ion. And just by convention, we put that charge in Roman numerals in the parentheses. So the reason that we're doing that is for sodium, we didn't need to specify the charge because sodium is in one of those columns where we always know what the charge is going to be. So by saying it's a sodium ion, you know that it must be +1. But for copper, we don't know without more information, so we have to put the charge. And then for monoatomic anions, all we do is we replace the ending of the name of the element with "ide." So bromine is in that second to last column. It has a -1 charge. And so we replace the bromine with bromide. So for cations, we don't change anything except we add the charge if we need it. And for monoatomic anions, we replace the ending with "ide." So when we have compounds based on these ions, there's always a cation and an anion, right? We need to have a neutral charge. And we just put the cation first. We leave out the word ion because now it's in a compound, and we put the name of the anion. So MgCl2 has a magnesium ion. Magnesium is in that second column, so we know that it's +2. Chlorine is a -1 anion. We change the chlorine to chloride, and it becomes magnesium chloride. So if I look at the name magnesium chloride, I don't need to tell you it's magnesium with 2 chlorines because you can figure that out based on the charges. So if I have MgCl2, I call it magnesium chloride. And if I just tell you the words magnesium chloride, if you know that magnesium is +2 and chlorine is -1, you know that it must be MgCl2. Does anyone have any questions on how to interpret or name these ionic compounds?
Well, hold on. So the name of the cation goes for cation goes first. So
Cation goes
Mg
first,
would be
yep.
the cation. Okay.
Yep. Any other questions? Okay. Just going to do some quick practice in the groups. I'll just give you a couple minutes. So we're going to name these compounds. So KBr, CuCl, CuCl2, and MgF2. So yeah, you just change the end of the anion to "ide." So bromine becomes bromide, chlorine becomes chloride, etc. Okay, go ahead and accept those invitations. I'll pull you back in just a couple minutes, so like 10:51. Okay, welcome back. I know that was super fast, so let me know if you have questions. But all we're doing is taking the names of the 2 ions, changing the anion to "ide", and specifying the charge if we need to. So this KBr is potassium and bromine. Potassium is always +1. It's not a transition metal, so we don't need to specify the charge. So this is just potassium bromide. For CuCl, copper is a transition metal, so we need to specify its charge. We can figure that out because the chlorine is always -1. So just like we did a couple slides ago, we know that copper has to be a +1 charge. So this is copper 1 chloride. If we didn't specify this charge here, we know it's copper and chlorine, but we wouldn't know the charge of the copper. And so we wouldn't know if it's CuCl or CuCl2 or what, because copper can have multiple charges. So for CuCl2, we know that the copper has to have a +2 charge. So that's copper 2 chloride. And then the last one is magnesium and fluorine. So fluorine becomes fluoride. Magnesium is always +2. It's in that second column, so we don't need to specify the charge. And so this is magnesium fluoride. Does anyone have questions on how I named these? Okay, so the other thing that happens with ionic compounds is polyatomic ions. So these are ions that contain more than one kind of atom. So poly just means many, and atomic is atomic. So polyatomic ions have multiple kinds of atoms. So there's this whole table. There's even more that aren't listed here, but these are the common polyatomic ions. You've seen some of these before when we were talking about solubility rules a couple days ago. Again, like, don't try to sit down and memorize these. I find that for me, the ones I use the most frequently, I sort of memorize by accident, and the ones that I don't use that often, I can just look up whenever I need them. So somebody may make you memorize these at some point, but I wouldn't do that until you have to. For now, you can always just use a table like this. And so these are just the names of these common ions. So sulfate is SO4 2-, etc. So if I have a name like calcium phosphate, I know that calcium has a +2 charge. I can find phosphate on my table. Phosphate is PO4 3-. And I know that I have calcium, which is +2, and my phosphate polyatomic ion, which is -3. I need my product to be charge neutral. So I'm going to need 3 calciums for every 2 PO4s in order to end up with a 0 charge result. So I will have Ca3 PO4 2. So getting the names of these, if you have the table, is pretty easy. You just, find the relevant one on the table. And then what we're doing to figure out those coefficients is just make sure the charge is neutral, just like we were doing with our neutralization reactions and our precipitation reactions. Does anyone have any questions on how I did this? So again, for now, I would not memorize the names of these ions, just use the table when you need it. Mostly for now, I just want you to be a little bit familiar with, like, you hear the word sulfate and you've heard that word before. Any questions on these polyatomic ions before I have you practice a little bit? Okay, so I am leaving the table up there. And so I want you to figure out the chemical formula of manganese 2 chloride, cobalt 2 hydroxide, and magnesium carbonate. I'm going to send the periodic table in the chat just so, in case you don't know the chemical name of manganese or whatever. Okay, I'm going to send you into your breakout rooms. I'll pull you back at like 11 o'clock or so. Okay, welcome back. Sorry, I know this is all super fast. Again, I just kind of wanted to give you a taste of the different naming rules. So for manganese 2 chloride, manganese is a transition metal, so we don't know its charge, but because we put this 2 here, that means in this case it's +2. Chloride is just chlorine, and it's -1, so I need 2 chlorines for every 1 manganese, which has a +2 charge. So I'm going to end up with MnCl2. This one's not a polyatomic ion, but no one's going to tell you, like, here's the name of a compound. By the way, it's polyatomic. So you have to be able to recognize them in different contexts. So cobalt 2 hydroxide. Again, cobalt is a transition metal, so we have to specify its charge. It is +2. Hydroxide, I can find on my table. It's OH. It has a -1 charge. So I need 2 of those for every cobalt 2 that I have to make it charge neutral. And then the last one is magnesium carbonate. I know that magnesium is +2. I can find carbonate on my table. It's CO3 2-. And so if magnesium is +2 and carbonate is -2, I just stick them together. I only need 1 of each in order for their charges to cancel out. Okay, so we're going to move on from ionic compounds in a minute. So I'm going to pause if there are any questions. to summarize, all we're doing is we're taking the cation and the anion and smushing them together. If the cation is a transition metal, we need to specify its charge because it could have multiple different charges. And the anion, if it's monoatomic, we just change the name of the element to "ide," so chlorine becomes chloride, etc. And then these polyatomic ions are just named how they are on the table. And when we're going from the names to the chemical formulas, we have to make sure it's charge neutral. Does anyone have any questions on dealing with ionic compounds?
Is the positive one always come first?
Yes.
Okay.
Good question. Okay. So for inorganic compounds, inorganic just means it's not based on carbon and hydrogen. So we'll talk about organic compounds in a couple slides. So for inorganic compounds, we don't have the cation and anion, so we can't just be like the positive one goes first like we just did. So we just go in order of where they appear on the periodic table from left to right. So if I have two elements together, I'm going to start with the one that appears farther to the left on the periodic table. Just like with ionic compounds, we're going to change the last one to "ide." So whatever comes last will change its name to end with "ide." And then in this case, because we don't have charges, we need to specify how many of each type of atom we have. So we're going to use these prefixes, which you'll see a lot in a bunch of different contexts. You might be familiar with some of them. Again, you don't have to memorize these, but mono means one, di means two, tri means three, etc. And so the reason that we need these prefixes now when we didn't before is before, if I had sodium chloride, I know that sodium is +1 and chlorine is -1, so I have to have one of each. I don't need to specify. But in this case, because they're not ionic, I don't have those charges, so I don't automatically know how many of each there need to be. So if there's, and this is just like a convention, if whatever comes first, if there's only one of it, we usually leave off the mono. But if you put the mono on there, like everyone will know what you're talking about. But just if you see the first one without a mono, you can assume that it's one. So just as some examples, technically H2O, which is water, you can also call dihydrogen monoxide. So hydrogen is farther to the left than oxygen. There's two hydrogens, so we say dihydrogen, and there's one oxygen, which means monoxide. So you might see some like jokes on the internet that are like, these chemicals are everywhere, dihydrogen monoxide, and it's like, it's just water. So people are scared of chemical names when like water is a chemical. So H2O is technically dihydrogen monoxide. SiO2 is silicon dioxide. So I left off the mono on that first one, but I could have said monosilicon dioxide and it would be the same thing. Does anyone have any questions on how I'm naming these? So I'm just going from left to right on the periodic table, and I'm putting prefixes to indicate how many of each type of element that I have. Okay. So I'm going to give you some quick practice. I'll send you into your groups for just a couple of minutes. I'll pull you back at like 11:10. Okay, so all we're doing is going from left to right on the periodic table and putting in our prefixes. So this is phosphorus with 3 chlorines. So I'm going to call it phosphorus trichloride. Again, I could have called it monophosphorus trichloride, but typically we leave off the mono if the first one only has one. So this is phosphorus trichloride. Phosphorus is to the left of chlorine on the periodic table. And then CO is carbon monoxide. So there's one carbon and one oxygen. So CO2 would be carbon dioxide. Okay, so I feel like this is a lot really fast. We're going to move into hydrocarbons or organic compounds on the next slide. So I'm going to pause. Are there any questions on what we've done so far? So for ionic compounds, unless it's a transition metal, when it's a transition metal, we specify the charge. And then once you know the charge of everything, you know how many atoms there must be of everything in order for your ionic compound to be charge neutral. So for ionic compounds, we never need mono, di, tri, because that information we can get from knowing what the charges are. So for ionic compounds, we just need to specify the charge if it's not constant, so like a transition metal. And then other than that, we just put the cation and then the anion. And if the anion's monoatomic, we change the N to ide. For inorganic compounds that aren't ionic, we don't necessarily know how many of each there are because they aren't charged. And so we need to specify the number of each type of atom. So we use these prefixes to specify the numbers of each. Any questions so far before we move into hydrocarbons? Okay, so hydrocarbons, maybe intuitively based on the name, are compounds that contain hydrogen and carbon. So they're called hydrocarbons. These are really common molecules in our day-to-day life. So alkanes are a word for hydrocarbons that have only single bonds, so no double or triple bonds. There are special names for the alkanes that have 1, 2, 3, and 4 carbons. These, like, you probably eventually will have to memorize. They kind of come naturally to me now because I've just used all of them so much. So methane has 1 carbon, and remember, a carbon always needs 4 bonds. So for methane, there's only 1 carbon, so the other 4 bonds are going to be hydrogen. Ethane has 2 carbons, propane has 3 carbons, and butane has 4 carbons. So I seem to remember when I first took chemistry, it was like I had a friend named Megan, and so we called it Megan eats peanut butter to go 1, 2, 3, 4, whatever works for you. You don't need to memorize these right now, but these are just special words for the alkanes that have 1, 2, 3, and 4 carbons. So alkanes have only single bonds, and these are the words for 1, 2, 3, and 4 carbons. If there are 5 or more carbons, we use the same prefixes as before. So if there were 5 carbons, we would call it pentane. 6 carbons, we would call it hexane. So these are the same prefixes we used for those inorganic compounds. So the prefix tells us how many carbons there are, and the ane at the end, so pentane, tells us that there's only single bonds. So if you remember, on day 5, we talked about line drawings. And so if you need review on line drawings, I'd recommend going back to day 5. We also reviewed it on days 6 and 7. So wherever a bond is drawn that doesn't end, that isn't specified what it ends in, it's a carbon. So I'll give you just a second to think about, count the carbons here and see if you can come up with the name of this molecule. So if I look for where all the bonds end, there's 1, 2, 3, 4, 5, 6, 7, 8 carbons. And so I just look at my prefixes, and this is octane. So if I had 9 carbons, it would be nonane, etc. Does anyone have any questions on how to name alkanes, so hydrocarbons that only have single bonds? Okay, so often hydrocarbons aren't these simple molecules with just single bonds. So in that case, we use alkenes. So with an E instead of the A, have a double bond, and alkynes have a triple bond. And so octane has single bonds, octene would have a double bond, and octyne would have a triple bond. We don't know where that double or triple bond is, and so we can put a number in front of the molecule to indicate where that double or triple bond happens. So I think this is clearer with examples. So this is octane from our previous slide. It has 8 carbons, so we call it octane. This also has 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. But the third one, 1, 2, 3, is where a double bond starts. So we call it 3-octene to tell us where that double bond is. And then if I had a triple bond, so this is octyne. This one's a little confusing because triple bonds, they're not bent anymore. So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So where that triple bond ends, there has to be a carbon there. So this is still 8 carbons. And then on the 1, 2, 3, third one, a triple bond begins. So that this is 3-octyne.
Wait, what? Wait, what? So 3-octine means it's triple bond, and because it looks like that, like a sandwich, it's a octine.
Because it has 8 carbons, we use that oct.
Okay.
So we count the carbons to figure out what prefix we use. So
okay,
octane, octene, and octyne all have 8 carbons.
Oh, so the 3 just showing like, yo, there's where it starts the triple bond.
Exactly.
Right? Okay.
So the oct means 8 carbons. The ending octane, ene, or ine tells us whether we have all single bonds, a double bond, or a triple bond. And the 3 in front tells us where that double or triple bond starts. So you're exactly right. So if I had 4-octene, that would just mean instead of being over here, the double bond would be over here. So the 3 just tells us where in my molecule that double or triple bond happens. Yeah, so counting the carbons with triple bonds is confusing. There's a question in the chat. So I think it's pretty easy to know there's a carbon here, 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 and here, right? Those are the sort of bendy bonds that we're used to. But if you look in the middle here, this triple bond ends. It ends right here. And this is a single bond. So there's a single bond and then a triple bond. So there needs to be a carbon where that triple bond ends and another carbon here. So there's 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 carbons. The oct means there's 8 carbons. So the Y is what indicates that there's a triple bond. So it's a little confusing in this case because there's a 3 here. So the Y is what means it's a triple bond instead of a double bond. And then the 3 in front, exactly like someone said in the chat, we count from left to right, and the number is referring to the first carbon where the bond starts. So 1, 2, 3 octyne. So the triple bond starts on the 3rd carbon. So just as a note, I'm going to look at octene just because it's a little simpler. If you counted from right to left, 1, 2, 3, 4, 5, that would be the same molecule. So if I just like flip this picture mirror image, it's the same molecule. And we typically just count for wherever the number is the smallest. So 3 octene and 5 octene would be the exact same molecule, because we can count 1, 2, 3, or 1, 2, 3, 4, 5. And we typically, our convention for, no good reason other than so we all are doing the same thing, the convention is that you count whichever way would make the number smaller. So you would call it 3 octene. So yeah, there's a lot of new words here. The oct is what indicates the number of carbons. So these all have 8 carbons, so they all have an oct in the name. The ending octane, octene, octyne tells us whether it's all single bonds, it has a double bond, or a triple bond. And then the number that we stick in the front tells us where that double or triple bond occurs. Thank you guys for asking questions. Does anyone have any other questions or clarifications on this? I think also just the line drawings part of it can be confusing. So you can also go back to the videos from like days 5, 6, and 7 to look at some review on the line drawings if you need that as well. And also, obviously, you can stay after class and we can talk about it. Okay. So I've smushed all the rules onto the left over here. So methane, ethane, propane, and butane are 1, 2, 3, and 4 carbons. And then the prefixes for 5 or more carbons are right here. And then alkanes, alkenes, and alkynes have single, double, or triple bonds. And we use a number to indicate where our extra double or triple bond is. So I'm going to give you maybe about 5 minutes to practice this. So I'll pull you back at like 11:29. And if you're watching this later, pause to practice. Okay, so again, don't panic. I'm really just trying to give you a taste of all of the different naming. It's okay if a lot of this is kind of foreign and new. They won't expect you in 1A to already be perfect at this. This will just maybe make it a little easier when you're learning it the second time. So the first thing we're going to do is we're going to count the number of carbons. So this molecule has 1, 2, 3, 4, 5, 6, 7 carbons. And so our relevant prefix is hepta. It has a double bond, so it's going to be an alkene. So it's going to be heptene. Its double bond is on the first carbon, so it's called 1-heptene. Questions on this? So our second molecule has 1, 2, 3, 4, 5 carbons. So it's pentene because it has a double bond. Its double bond is on the second carbon. So it's going to be 2-pentene. And then this last one is tricky. So it has 3 carbons, 1, 2, 3. So it's going to be propane. It has a triple bond, so we're going to make that ane and ine, so it's going to be propyne. And then we put a 1 because it's on the first carbon. So in this case, actually, if I only have the 1 triple bond, The mirror image molecule is exactly the same. So if I put the triple bond on the second carbon, the molecule would be the same. So if you want, you can leave off that one, but you don't have to if that's confusing. Okay. Does anyone have any questions on how I named these hydrocarbons?
Wait, is the third one, is that 2 carbons or 1 carbon?
The third one is 3 carbons. So there's 1, 2 on either side of the triple bond, and then this is a single bond. So there's a third carbon here.
Oh, okay.
So, yeah, so wherever there's a bond, there needs to be a carbon on both ends of that bond so that this triple bond ends. And so there has to be a carbon here. So there's 1, 2, 3 carbons.
Okay, thank you.
Yep. Any other questions? Thank you for asking. Okay. The last nomenclature thing I want to talk about is functional groups. So a functional group is just a thing that we can stick on to hydrocarbons. And they're called functional groups because they often add some kind of functionality. So for example, if I add an OH group, this R just means other stuff. So when I'm describing my functional groups, I just stick an R there to say there's something here, but the thing that I'm looking at is whatever else is there. So this is an OH group attached to anything else. And this we call a hydroxyl group. This helps, this makes our molecule an alcohol. So we put an OL in the name. So I'll give you an example. This molecule has 1, 2, 3, 4, 5 carbons. So that means that it's pentane. There's no double bonds, so it's just pentane, not pentene or pentyne. And then it has this OH group on the third carbon, 1, 2, 3. So just in the same way that we indicated where the double bonds were with a number, we're going to indicate where the extra group is with a number. So this hydroxyl group is on the third carbon. So we put a 3 right here. And we change the ending from pentane to pentanol to show that there's a hydroxyl group, and that's what that 3 is referring to. So just like we had double bonds or triple bonds on the previous slide, in this case, we are sticking some extra group, in this case, a hydroxyl group. And we put a number at the beginning to indicate where that extra group is being stuck, so which carbon it's on. And we change the ending to indicate what kind of group it is. So the 3 tells me there's something going on with the third carbon, and the all on the end tells me that what's going on with that third carbon is I've added this hydroxyl group, this OH. Yeah, so there's a question in the chat about what you would do if there's multiple. It gets real complicated real fast. So there's rules about if there's multiple groups, which ones go first. If there's 2 double bonds, what happens? It gets really complicated. So for now, I just want you to focus on what happens if there's one fancy thing going on. But like, if there were 2 double bonds, you would put both numbers in front of the name and you would call it like pentadiene to mean that there's 2 double bonds. So it gets real complicated real fast. And I'm sorry. So just as another example, this is an amine group. So we have R, which means some other stuff, and an NH2, which is our new functional group. So we put amine on the end of our name, just like we put all on the end of our name in the previous case. So if I have this molecule, I want you to just take 30 seconds and think about what you would name this. Okay, so this has 5 carbons, just like before. So it's pentane. It has an amine group on the 3rd one. And so I'm going to call it 3-pentanamine. So pentanol was with the alcohol. We keep the pentan, P-E-N-T-A-N, to indicate that we have 5 carbons. And then we add that amine on the end. So this is 3-pentanamine. Any questions on what I'm doing here? Okay. So there's a whole lot of functional groups. This is just a few examples of common ones. Do not try to memorize these right now. A lot of these I don't have memorized and I have to go think about. But the point is that if someone gives you this table and you know what the functional group means, then you can follow the same rules as before on how to name a compound that has that functional group on it. So for now, my goal is for you to just start recognizing some of the names of molecules and know that, like, if I gave you a table, if you could look up what an amine group is, you could figure out what these molecules are, or at least you won't panic. You will have seen these before. Does anyone have any questions on any of the nomenclature stuff we did today? We're going to switch gears in a second.